So thanks for the conference. It's been really great. So this paper is this conference about business cycles. So I have to tell you what this has to do with business cycles. So this has to do with vector autoregressions, like Chris Sims was talking about this morning, and vector autoregressions, as Chris told us this morning, tell us something about business cycles. So therefore, this tells you something about business cycles. It's a bit removed, from the immediate focus of the conference. But I hope it turns out to be useful for those that empirically use vector autoregressions to think about identified shocks and things like that. So let me tell you what this paper is up to, and I'll try and give you an overview, and then sadly we have to sort of go into the weeds, and then there's some like algebra we have to look at, and once we look at the algebra, we'll go, oh, that's easy. Now we understand it, and it's clear, and then we're done, right? So first, let me tell you what this is. Okay, so we know, Chris talked about this, this morning, and obviously people have been talking about it for 30 some years, which is, the identification problem in structural vector autoregressions. Okay, so there's that problem, right? And so that's kind of Sims, and then there's one way to think about solving this problem, which I associate with Romer and Romer sort of in thinking about monetary policy, sort of instead of looking at VARs directly, reading some minutes, doing some historical work, and finding some which they characterized as exogenous movements in monetary policy. Determined by things outside the vector autoregression or related to things outside the vector autoregression, and in their case, reading minutes of the Federal Reserve. So we've got, structural vector autoregression Sims. We then have something outside the vector autoregression, which tells us something about some shocks. I'm going to call these exogenous. I'm going to call these external instruments, and so that's what external means in the context of this talk. And then we're going to use these to identify shocks in what will be a very natural way, and that'll be straightforward. The interesting part, interesting in some way anyway, of this, the part that makes this a little bit non-standard is it turns out that when you try to do this, as Jim Stock and I tried to do last year in a paper, many of these, interesting exogenous instruments turn out to be weak, turn out to be useful. That is, they're sort of correlated with the shock of interest, but they're not very highly correlated with the shock of interest. And that leads us to think about doing inference in a way that's, familiar from the sort of Steger and Stock and Morera kind of analysis. So I kind of think of this paper as, Morera meets Romer and Romer meets Sims. So that's what that's what we're going to do here. Okay, so that's the overview. So now we have to just work. Apologies, late in the day, but sometimes work late in the day is good for you, right? You have two choices. You can sleep, right, or work. So you can sleep or work. Your choice. Okay. So I'm just going to go through the notation. Okay. So here's what. Okay. So that first equation up there, that's just that's a reduced form vector autoregression. Okay. So y depends on lagged y's, and these etas are one step ahead forecast errors. Okay. And this VAR is whatever pth order. The notation y is going to be r by 1. So there are elements in this vector autoregression. In Chris's thing this morning, there were 6 or something like that, right? And then the challenge is we're going to think about this model as being invertible, right? So we're going to think about these etas as depending on some structural shocks epsilon, right? Through some matrix that we don't know H, right, where H is going to be non-singular. So if we knew what H was and we had eta, right, we could get these structural shocks and you know, we could identify these monetary policy shocks or other shocks that you know, Chris was interested in thinking about looking at this morning. Right, so our challenge here, you know, our challenge is going to be to go from the etas to the epsilons and compute the usual kinds of things that we want to compute in vector autoregression. So just to sort of finish up the notation, so eta is are the reduced form errors, epsilon are the structural errors, H is going to be this important matrix that links these things, and H has columns, you know, H1 ... HR, and this epsilon, there are of these structural shocks. This is going to be important because we're going to try, we're going to be, we're not going to be very ambitious here. We're going to do analysis kind of like, we're going to do this. We're going to think about identifying just one of these shocks, like a monetary policy shock, or an oil shock, or a commodity price shock, or something like that. That's what we're going to be interested in, just one of these. Right, so we're not going to be ambitious and try and get all of them, try and understand the complete structure. We're just going to be interested in one of these guys. So we're going to call it epsilon 1. We'll call it the first guy, right? And it's going to be related to eta by this H1 thing. Okay, so YT is A of L, YT minus 1 plus eta T. Eta is just H times epsilon, right? So you could, you know, so this is what you get, right? What Chris would call a structural vector autoregression. Chris was discussing a paper of mine a while ago, and I think I put this equation up, or like it, and he said, no, that's not a structural vector autoregression. Anyway. No, he's shaking his head, but anyway. He said something else I did wasn't, but okay. So, we can take this thing, you know, we can take this thing and invert it, right? And then that'll give us the moving average representation, which tells us how, you know, how these shocks affect Y dynamically. So this C of L times H thing, these are the dynamic causal effects that we're going to want to get at. Okay, so this is just, you know, this is just the same notation. Now I want to make it clear, you know, that we're just interested in this first shock, epsilon 1. So YT is going to be a distributed lag of epsilon 1, right, which is going to, and figuring out is going to require knowing the first column of H. The C of L thing, this is just these C weights that come from the vector autoregression, so we know those or we can estimate those. H1 is going to be the important thing. And then these are these other structural shocks, which I'm not going to try and identify, okay? So I'm going to focus just on this thing. Okay, and as I said, we know these C things. Okay, so so when we have that, right, so what's the standard what are the standard calculations that people do, right, when you run vector autoregressions, right? Well, you know, I guess you know, a standard thing, you know, going back to, you know, Chris's famous 1980 paper, right, is you might want to compute dynamic multipliers or impulse responses, right? So what are those going to be? So this is just the derivatives of you know, the jth element of Y with respect to epsilon 1 k periods ago. That's going to depend on the C thing that we know, and it's going to depend on H1, which we don't know. So this H1 guy, again, is going to be important. We might want to do historical decompositions. We might want to know, you know, in 2009, output was really low. Why was output really low? Was it really low because there were, you know, some liquidity, some identified liquidity shocks, or was it very low because there was still a hangover from high oil prices, or, you know, did the drop in oil prices lead to an increase in output that we wouldn't have seen, right? So that's what we get from these historical decompositions. Notice that requires a couple things. It requires knowing this H1 thing, right? And also knowing this epsilon thing, right? So we've got to know both of those, right? And then we might want to know sort of things on average, right? How much of the variability in output over the business cycle comes from, you know, oil shocks? How much of it comes from monetary policy shocks, et cetera, right? So that's sort of variance decompositions. Okay, so we're going to think about, I call these VAR estimands. That is, these are the things we want to estimate, right, when we do this VAR analysis, right? So I'm going to focus on estimating these guys, right, in a situation that's a little non-standard. Okay, so this is what, you know, here's a standard way of doing it, right? It's the way that, well, it's this, right? So you take your vector autoregression and then you make some identifying assumptions, right? Maybe some short-run restrictions like, you know, Sims 1980, or long-run restrictions that people have messed around with are, you know, I guess today we saw identification through heteroscedasticity, right, that you've seen, right? And, you know, on impulse responses, but these are sign restrictions, if you will, right? So, you know, so that sort of thing. So you could do, oops. Oh, test, yeah, okay. So you can do it that way, right? And so we're not going to do it that way. I mean, that's a good way to, we're going to do something else, right? So we're going to think about, this, you know, external information or external instruments. So, right, you know, I mentioned this, you know, Romer and Romer is a, you know, classic example of this. Another classic example of this that I'll be looking at is, you know, Jim Hamilton's work or Lutz Killian's work on oil price shocks, right? So think about Killian's work. You know, Killian did careful work studying OPEC to measure shortfalls in production associated with exogenous events like wars. Okay? So those are exogenous changes in supply that we might think have some effect on price, that we think might then have some effect on output. Okay? So let's think about, you know, if we had some of this external information from Killian, OPEC supply shortfalls might help us determine, you know, what price shocks are in, you know, oil price shock, the effect of oil prices in a vector autoregression. And this kind of way of thinking about, you know, looking for exogenous shocks, you know, has been used, well, you know, Romer, a lot of work on monetary policy shocks, and be familiar literature to many of you, some work on fiscal shocks, again, by Romer and you know, Valerie Ramey's work, et cetera. Fisher and Peters as well, you know, some uncertainty work, some work on liquidity, and of course the work on oil prices. So okay, so what we're going to do is we're going to look at these guys. Okay, so if you know this empirical work, you know this is the way these guys usually do this. You have one of these identified external instruments, let's call it Z, right? Like an oil price shock if you're Hamilton, right? And then what do? You regress output or inflation or something on a distributed lag of that shock, right? And you report those coefficients, right? If you think about this in the context of this vector autoregression, or in the context of, you know, a standard simultaneous equation model, what we want to do is we want to estimate a structural equation, right? And we have an instrument, right? What those regressions are those regressions are, you know, the first stage of two-stage least squares, right? You run those regressions first, you find how the endogenous variables respond to the exogenous variables, and then you put that information together, right, to find the structural responses. So what we're going to do here is we're going to think about, we're going to think about this. We're going to think about this using these guys as instruments in kind of a two-stage least squares kind of way. Now, this paper isn't the first to do that. Jim Hamilton did this in a nice way in a 2003 paper, and you can see Lutz's work in this in 2008. Jim and I had some work in earlier, and there's two nice papers by Carl Mertens and Morten Ravn that do this. And their setup, as it turns out, is going to be very similar to what we're going to do here. We're going to handle some weak instruments that they don't. But if you know this work, most of what I'm going to do here for the first half hour or so is going to be familiar to you. And if you haven't read these papers, you should read these papers. Are really nice. It's great empirical work. Okay, so as I said, we got interested in this because we tried to use these external instruments to identify shocks in a factor model, and this. So here was the empirical exercise. We were studying the the last recession that went on in the United States. And the question was, why did it happen? What caused output to move? What caused a whole bunch of variables to move? What caused inflation to stay high, et cetera, right? What were the important shocks? So, you know, in a paper that, that we wrote in Brookings in 2012, we, you know, took basically the setup. We had, you know, a whole bunch of variables X, and we related those to some factors F. So this is kind of like Eshwar's work earlier today, or at least the statistical model is similar. The factors were latent but followed a vector autoregression. So this is the same eta that I had on the last slide, right? And then we can think about this eta as, you know, depending on some, you know, structural shocks, monetary policy shocks, liquidity shocks, financial crisis shocks, oil shocks, et cetera. And so we wanted to find out how these guys affected X, right, these observables, right, during, you know, the Great Recession. To do that, what did we do? Well, we tried to use external instruments to identify some candidate shocks. So we were interested, you know, at the beginning of the recession, there were questions, you know, were the high oil prices in 2005, 2006, beginning in 2007, responsible for if I spoke in Portuguese, I bet they would just keep working. There's only so much translation that these things can do, right? Runs the batteries down. Okay, but, you know, so oil shock, we were interested in looking at monetary policy shocks. You know, productivity, you know, might have been important in this recession. You know, uncertainty, liquidity, fiscal policy were all things that might be, you know, important. And looking at the past literature, you know, you could see, you could find some external instruments external to what we were doing here that we thought would help us identify those things. And then the question was, you know, how do you do inference in these settings? So that's what led, you know, to the work that I want to talk about right now. Okay, so here's the basic mechanics, right, of what we're going to do and the problems that we're going to run into. So, you know, let's think about Z as being a vector of instruments. So Z is like we're interested in finding a, you know, the effect of oil prices. So Z is going to be an external instrument for oil prices. Okay, so this is like, you know, Killian's OPEC supply shortfall, right? And we might also have, you know, Hamilton's measure of oil shock. So we might have two Z's that tell us something, right, about oil prices. Right, and we've got, here's so that's some data that's given to us, and we have eta, right, which are these one step ahead forecast errors which come from this vector autoregression. And, you know, this vector autoregression, this is this reduced form thing, we can just estimate that, right? You just estimate that by running ordinary least squares, right? So this guy's really easy, so we can estimate, so we can get these shocks that, you know, we can estimate these shocks, and we can estimate, you know, this guy inverse, so we can get this distributed lag. So we know C of L, and we know eta, right? And the challenge is going to be, right, to do this, to estimate these impulse responses, historical decompositions, variance decompositions, et cetera, given this information. So what are the observables here, right? The observables here at the end of the day is we know Z and we know eta, right? And I guess we know C, right? So what I want to do, right, the first thing I'm going to do, you know, the first part of the econometric exercise is to write out what I want to estimate, these estimands, right, as a function of the, you know, the variance of the etas, the variance of the Z's, and the covariance between eta and Z, right? Because those are things I can compute, right, with the data. Okay, so let's just do that. And I'm going to need some identifying assumptions to do that. Here they are, right? So there are three of them. Three of them, yes. Okay, so what are they? Well, they're the first two are the usual, you know, if you take Econometrics 101, right, and you have an instrument, and this is, I'm in Brazil. Okay, so if you take Econometrics 101, right, you should use a good textbook. I always ask people how many good textbooks are there, right? And the answer is one, right? And everyone here in Brazil knows that, right? Because I looked up, before I came here, I looked up, for some reason, I've sold 50,000 copies of this stock Watson textbook translated into Portuguese, right? And that's got to be, everyone in Brazil owns a copy of this book. So everyone knows these equations, right? Because they're there, right? So the first equation is, an instrument's got to be relevant. It's got to be correlated with the thing you're interested in. Here we're interested in epsilon 1, so Z's got to be correlated with epsilon 1, right? The covariance between epsilon 1 and Z I'm going to call alpha, right? And that can't be 0, right? So that's relevant. This guy's got to be exogenous, right? It's got to be uncorrelated with the other structural shocks, right? It better be the oil instrument tells us something about oil, but it's not telling me something about monetary policy, right? A monetary policy instrument better telling me something about monetary policy and not something about fiscal policy, right? Or this analysis will get confused, right? So that's what this is. So relevance, exogeneity, right? And then I'm going to want these shocks to be uncorrelated with one another, like Chris was talking about earlier today. Okay, so now we can think about, identification here and, the things that I want to estimate, right? I talked about estimating H1, right? It was this first column of H, which told me how to go from, etas to figuring out what epsilon was, right? So how do you do this? Well, it's pretty easy now. Write out the covariance between eta and Z. Well, eta is just H times epsilon, right? So that's the covariance between H, epsilon, and Z, right? So that's just all of these H's times the covariance between epsilon 1 and Z, epsilon R and Z. This guy is equal to alpha. All those other guys are equal to 0, right? So that's just going to be this guy, right? So you can see, right, if I've got one Z, alpha is just a scalar. So this guy is H1 up to scale. Right, so I kind of got H1 at least up to scale just from this, simple covariance, right? And then there's the question, how to identify the scale. Now this turns out to be, I can see this guy, but obviously I can multiply alpha times 2 and divide H1 by 2, right? And that's going to cancel. So that, I got to determine the scale sum here. Here, typically it doesn't matter. It's going to actually matter in some of the calculations I want to do. So I want to talk about the normalization here. What we're going to do is set H11 equal to 1. So what does that mean? That means that what we're going to do is I'm going to think about the size of this shock in terms of its impulse to the first variable. So think about Chris's, I looked carefully at Chris's numbers when he had them up on the board today. So this is what Chris's numbers were. He had his monetary policy shock. What did it do? He put up all these impulse responses, right? His monetary policy shock on impact moved Fed funds up by 50 basis points. And then after a while, it moved output down by 30 basis points, right? And so the way you think about that is it was a 50 basis point move in Fed funds led to a 30 basis point movement in output. So you what matters are the relative values of those two things, right? So we're going to set this equal to 1. This is going to say we're going to think about, if you will, 100 basis point move. We're going to think of shocks that are of the size that they lead to 100 basis point movement in the federal funds rate. Okay? So that's what this is. So we're going to get the units right. Okay, so that's what that guy is. Okay. Okay, so boom. Well, so now we're done, right? Remember I said, we could identify H1 times alpha, right? And now I know H11 is equal to 1, right? So that means, the covariance between the first eta and Z must be what I'm going to call alpha. So that means H1 is just going to be the covariance between eta and Z divided by the covariance between eta 1 and Z. Right? So that's identified an object. So that's given us our impulse responses. Okay, so now those of you that have taken Marcelo's courses, right? Now you're done. You look at that and you go, oh, right? There's this thing in the denominator, right? And, right, if I have a weak instrument, if this guy is weakly correlated with this guy down here in the bottom, in the denominator, right, is close to 0 or something, right? So I have to worry about a divide by 0 problem, so I've got weak instruments, right? If I have weak instruments, right, it's gonna show up right here. So this is exactly, right, why this problem turns out to be interesting. Okay, so now, this is like the worst slide here. Okay, but I like it. So this is figuring out these historical decompositions, okay? So what do you want to do now? I want to find, right, I care about finding out what H1 times epsilon 1 is. So now I not only need to know H1, but I need to know what epsilon 1 is, right? How do I get that? What's the information I have? I have eta, and I have z, right? And I guess I know H1, right? But how do I get epsilon 1? Well, you know, it turns out to be pretty easy, right? So you just, here's the logic, right? What is H1 times epsilon 1? Well, that's the projection. If I ran a regression of eta on epsilon 1, that's what I'd get, right? Well, the projection of eta on epsilon 1 is, of course, the same as the rejection of eta on b times epsilon 1 for any number b, right? That's nothing, right? Well now, okay, let's go back up here, right? Let's look at the projection of z onto eta. This is a regression I can run. I can regress z onto eta, right? What's that going to be? Well, eta is just a linear combination of the epsilons, right? Where that's invertible, right? So the projection of z onto eta is the same as the projection of z onto epsilon, right? Well, z is uncorrelated with all of the epsilons except epsilon 1. So the projection of z onto epsilon is going to be the same as the projection of z onto epsilon 1, right? So that's just going to be b times epsilon 1, where b is the regression coefficient. So regressing z on eta gives me b times epsilon 1, right? And regressing eta on b times epsilon 1 gives me this thing that I want, right? So what do I want to do? I guess I want to project eta on the projection of z onto eta, right? So this just gives me the formula for what H1 times epsilon 1 is going to be. It's just this object, right? Where where this lambda guy turns out to be this ugly expression. It's not an ugly expression, actually. It's a beautiful expression, right? Marty said yesterday, you know there's a God when things look nice and, yada, yada. God exists, okay? Right, QED. Okay, so now you can see again, right, that we're going to have, again, if you're Marcelo, right, you can see again there's going to be a problem because this guy down here is inverted, right, and these guys might be close to 0, right, if you've got weak instruments. Identification of these variance decompositions, I have to compute the variance of that top thing. That requires the variance of this, right? That simple calculation shows you that it's that same lambda guy. This beautiful expression from God. Okay, now okay, so I said those are the things that we want to estimate. Sometimes there's some things you might want to test if you're doing, if you were like doing one of these models. This is what you'd want to test. This is what Jim and I wanted to test when we did this Brookings thing, right? Sometimes researcher A says, I have a monetary policy instrument. I read the minutes of the blah and it's this, right? And someone else says, I have a monetary policy instrument. I did some modeling over here and I've got that, right? Well, if both of these guys are right, you can identify the monetary policy shock using instrument 1 or instrument 2, right? And you better get the same monetary policy shock, right? So that says there's an over-identifying restriction that you want to test. At the covariance between eta and z, these two z's, right, is going to have rank 1. So you want to test that. Okay, so that's one thing you might want to test. Another thing you might want to test is if some researcher says, I got a monetary policy shock, a monetary policy instrument. Another researcher says, I have a fiscal policy instrument. You can identify the monetary policy shock. You can identify the fiscal shock. these things should be uncorrelated with one another, right? If the model's right, if the instruments are right, right? So you might want to test whether, you know, two instruments for two different shocks lead to shocks that are uncorrelated with one another, right? So those are the sort of tests for over-identifying restrictions, right, that you might want to look at. Okay, so let's just do that. I'm going to forget about, for the purposes of this discussion, I'm going to forget about lots of things, my name, but I'm going to forget about estimating the VAR coefficients, right? We know how to do that. We know how to do inference there. So I'm going to just forget about that. Okay, so let's just suppose you know those guys. Okay, so then what's going to be key to us, right, is you know, this covariance between eta and z, right? That's where all the action is, right? That's where this matrix from God came from. That's where H1 comes from, etc. Right? So, you know, we have, you know, we're going to estimate this by method of moments, right? So what's our key moment condition? Well, you know, z times eta, you know, that, well, the expected value of that's that, right? So we want to estimate that guy, right? And then turn that into estimates of things that we want. So we're just going to assume, you know, to do the inference, we're just going to assume that, you know, that this guy satisfies the central limit theorem. So we'll use the typical normal asymptotics that you would use in GMM, right? Kind of things that, you know, you learn in any good undergraduate textbook. They're just one of those, right? And you can get it in Portuguese, okay? I don't know how we sold. It was actually not 50,000, I exaggerate, but it was like 48,244 Portuguese translations of this book. I mean, it's a pretty good book, but that's a lot of books. Anyway. Okay, so we're just going to do GMM, right? So let's think about, you know, let's suppose the model's exactly identified. Well then, you know, how do you estimate the covariance between eta and z? Well, it's the sample covariance between eta and z, right? So that's going to be our estimator. That's our GMM estimator. Simplest thing, it's just standard method of moments from, you know, econometrics 101. If k is bigger than 1, then you want to do some reduced rank regression stuff. I'm not going to talk about that. Okay? And remember, this sigma a to z kind of has this structure. Okay, so now, you know, I've estimated, you know, sigma a to z. I'm just going to use this method of moments thing, right? Remember H1, right, was the covariance between eta and z divided by the covariance between eta 1 and z. So that's going to be my estimator for H1. Okay, so, you know, again, you can see why you're going to have a weak instrument problem here as you look at this. Here's an IV interpretation. But okay, so now if you want to do inference for this thing, everything's set up. If you want to do inference for this thing, if you've got, if these z's are strongly correlated with these etas, this is just a GMM problem. Everything is nice. Everything's been laid out here. Everything, all the little formulas are worked out. You just do GMM. You say estimate, test over identifying restrictions. You say test over identifying restrictions, and it gives you stuff, and everything is, you know, completely regular, and everything's everything, right? So there's nothing new here. Okay, so that's fun. So you can see this, examples of this again, you can see in the Hamilton paper, the Killian paper, and in particular, the Mertens-Raven two papers that I mentioned. So they're going to do this. So what we're going to focus on is what turns out to be what is sometimes an empirically relevant case, cases in which these etas and z's are correlated, but not really very highly correlated. So the weak instrument problem of the sort that Marcelo's worked on, and that turns out, you know, that we know from, you know, work of people in, you know, doing instrumental variable estimation in lots of areas in economics and social science generally, you know, turns out to be important. Okay, so whoops. Right, so now what are we going to do? Well, so now we're going to assume, right, remember this covariance between eta and z I called alpha, right, but now let's make it small. Right, and for those of you that have studied this, right, you know what it means to make it small. You need to make it, you need to sort of think about this guy in some in some neighborhood of 0, right? The square root of the sample size, neighborhood of 0. So we're going to think about gamma as a parameter that's going to be interesting to us. It's going to be alpha, but after you scale it up by the square root of the sample size. So gamma is going to tell us how weak the instrument is. In the usual strong asymptotic world, gamma is a really big number, right? And here we're going to think about it being potentially a small number. This central limit theorem result here, which looks at the average of z and eta minus its expected value as normally distributed, then translates in this weak instrument world to the covariance between z and eta, unnormalized, right? I haven't subtracted off its mean. This guy's a normal, and gamma turns out to be the mean of this guy, right? And it's got some covariance matrix omega. So I want to think about, these are going to be the data that I'm going to view that as a draw from a normal gamma omega distribution, and then we're going to think about estimating things. Okay, so this is Jim Stock's slide. He always makes them look like this. So you can see what's going to happen here. Here's our H1 hat thing. It's the average of this guy divided by the average of this guy. This guy's normal, gamma something. This guy's normal, gamma something, right? So this is going to be a ratio of two normals, right, where they got different means. So that's what this thing says, right? In the normal world where you think about, asymptotics in the usual case, we'd have something like sort of like that, right? We would have a normal divided by a constant. Now we got a normal divided by a normal. And, and as you know, that's what gives rise to all the weirdness in this weak instrument stuff. So here's a couple of things that will look familiar to you. Again, that should look familiar to you from this weak instrument stuff, right? The weakness of the instrument depends on, a parameter that you can sort of estimate that's related to the, first stage F statistic of the regression of eta 1 onto Z. If eta 1 is weakly correlated with Z, then when I regress eta 1 onto Z, I'm going to get an F statistic which is, small. If eta 1 is very highly correlated with Z, I'm going to get an F statistic that's big, right? And that, a rule of thumb is, the weak instruments are important if the F statistic is smaller than 10. Here's another result that you get that's not obvious. Well, I guess it's obvious once you see it, but it wasn't obvious until I saw it, right? Which is, here's the result. Let me state the result. And then, okay. So suppose I use an instrument that's not only weak, it's useless. I just made it up. I got it from a random number generator. And I go out and do this analysis. I estimate impulse responses, variance decompositions. I identify, the structural shock, and I identify it as the shock that leads to a 1 unit effect on Y1, the first Y. Well, as it turns out, I've used an instrument that's completely useless. You might think that, who knows what I'm going to get out of doing that exercise. Well, it turns out that the median of the estimator for that shock is going to turn out to be, it's going to be as if you did a Cholesky decomposition, and the shock that you're going to identify is the shock that's ordered first in a Cholesky decomposition. So you might think you did instrumental variable stuff, but really all you did was a Cholesky factor, right? So this isn't obvious. This is sort of obvious. Anyway. This is a familiar result actually from two-stage least squares. This slide says something. So now I'm going to show you something. I'm going to show you some numbers. These are from simulations. I'm going to go through them quickly. So here's the simulations. GDP and oil prices. Ken, I want to look at the effect of oil shocks on oil prices and on GDP. Okay, and so these are going to be simulations. This is calibrated to U.S. data and using Killian's oil price measure. Okay, so I'm going to show you some impulse responses. So here's the first one. So this lambda 1 thing, this is a measure of how strong the instrument is. Lambda 1 squared is equal to 100. It's really strong. Okay, so here are the results that we get. Here's the true impulse response, right? And here are some bands. I did this, a couple hundred times, and this is what you get, right? So this is a sampling uncertainty, if you will, around it, right? It looks kind of normal. Everything's kind of nice. Here's what happens when you have weak instruments, right? Lambda 1 squared is now equal to 1. You get wacko stuff, right? So this is the weak instrument thing, showing its ugly face, and here are sort of things in between, right? You get familiar kind of, things that are skewed, but with, crazy outliers and stuff like that. And things in between, and then, here's the effect of, oil prices on output. That's in the nice world, right? And then it's wacky, right, if you happen to have a weak instrument. Okay, so I'm just going to go through that. You can do this for these weak instrument asymptotics, not only for impulse responses, but for historical decompositions and variance decompositions. Again, that's going to depend on the behavior of this, lambda thing. That's this matrix from God. And I'm not going to show you that. You could work it out, though. Now here, this is from this empirical paper that Jim and I wrote that led us to start thinking about this. So remember, what we were trying to do is we're trying to find what were the important shocks that caused the recession that we just went through in the United States. We were using, a lot of external instruments, right? So here's this F statistic. This F2 is this F statistic, which is measuring whether these instruments are weak or not, right? So F statistic bigger than 10, maybe it's not a big deal. F statistic less than 10, maybe these weak instruments turn out to be important. You can see here for the various, when we use the Killian oil shock, you see the F statistics are tiny, right? So weak instruments are going to be a problem there. If you use, here a variety of things. If you use, the Ramey spending shock for fiscal policy, turns out to be a very weak instrument. Is not going to identify very much here in our setting. And the same thing's true if you were using Romer and Romer taxes, et cetera. So many of these instruments turn out to be weak, and so inference is going to be non-standard. Here's something else that's interesting that we found disturbing when we looked at it. Okay, so this is what we did in this paper. We estimated all these shocks, monetary policy shocks, fiscal shocks, oil shocks, again, which of them were important during this recession. And this is what we found. Here's the identified monetary policy shock using Romer and Romer instruments. Here is the oil price shock using Killian's external instrument for oil. Here's the correlation between those two structural shocks, 0.65. So the monetary policy shock and the oil shock are not uncorrelated. They have a correlation of 0.65. Here's the correlation between the monetary policy shock identified using Romer and Romer stuff and the fiscal shock identified using Romer and Romer stuff. Those are two separate papers. Here's a paper in which they did fiscal stuff. Here's a paper in which they did monetary policy stuff. If you put those two things together and you computed the two different shocks, you'd find out that they had a correlation of 0.77. They weren't different things. They seemed to be the same thing. So a question is, are you disturbed by this? We thought this was just silly. That these guys had written two papers, but they were really just the same paper, right? And the question is this 0.77 number, is this big? Would you be surprised to see this if you had weak instruments, right? Or is this just a symptom of weak instruments? The shocks are really uncorrelated, right? But the estimated shocks turn out to be highly correlated because the instruments are really weak. Okay, so what one needs to do is to go through and work out the distribution of sampling the distribution of the sample versions of these. If you got weak instruments, that's done here. I'm not going to take you through this, but the bottom line is you can have you can find shocks that appear to be very highly correlated, even though the instruments are valid, if they turn out to be weak. Right, so one has to do inference here very carefully. I'm not given the time. I'm not going to go through that. Let me just go through one thing here. I want to talk a little bit about how you do the right inference when you got weak instruments. If you've got weak instruments, they're not useless. They're just not strong, right? So you can't do inference using the usual GMM stuff, right? That would lead you astray. Tests, you can't use tests based on that. You can't construct confidence sets based on that. So what we're going to do is, think about doing weak instrument robust inference, a subject that, has been studied deeply in sort of standard simultaneous equation models by Marcello and others. There are three ways to do it here. I'm just going to show you one of them. I'm going to hop through this. Given the time. Okay, so let's just do it for impulse responses. It turns out to be pretty easy for impulse responses. So impulse responses, remember, are, what's the, there was a formula 53 slides ago, that said, the impulse response for variable h at horizon j was this thing, right? So if I want to test whether this impulse response is equal to 2, right? I want to test whether that guy is equal to 2, right? So, what's H1? Well, remember H1 is just, it was the covariance between Z and eta divided by the covariance between Z and eta 1, so that's this ratio. So saying that that guy's equal to that guy, saying that that guy minus that guy's equal to 0, and then I can carry out a standard test, right? So this turns out to be, this turns out to be in the jargon of this literature, this turns out to be, an Anderson-Rubin test, right? And, we might just want to invert it to construct confidence sets. That turns out to be the best thing to do in this just identified case. When you've got multiple Z's, you might want to do something better. So you might want to use a Morera kind of conditional likelihood ratio test. You could probably even do better than this, because there's some invariance to this eta thing, right, that you'd want to worry about in this setting. We haven't done that yet, but we should do it. Let me end by just showing you some numbers. So these are impulse response functions so this comes from this Brookings paper, of GDP, the GDP deflator, employment, with respect to an oil price shock. So what this oil price shock does is raise the price of oil by 100 basis points, reduce GDP, raise prices, reduce employment. These are quarters down here. This oil price shock is identified using Hamilton's oil price measure, and the F statistic turns out to be 15. That's a big number, so this is a pretty strong instrument. You can see around these impulse responses, you can see error bands, and I got 2 error bands here. I got error bands that you would compute using GMM, the usual strong instrument stuff. I think that's the dashed lines, and the solid line are the weak instrument, robust error bands, right? And you notice those are basically the same here, right? Now let's suppose you were doing something like this. This is identifying the same shock, but using Killian's instrument. Well, now the F statistic isn't 15 anymore, it's 1, right? So this is a weak instrument. And now what you see, for example, is here's the estimated impulse response for GDP, right? Here are the error bands you would use if you thought that you had strong instruments. Here are the right error bands, or the error bands that would be appropriate if you had weak instruments, and here you have weak instruments. So here, the weak instrument robust stuff turns out to be important. Monetary policy shock. I'm not going to go through this. I'm just going to conclude now by saying that we have more work to do there's always more work to do. But we have particularly more work to do. I'm not going to take you through this. I guess what I want to do, though, is, what I learned from this exercise is, this external instrument stuff is pretty neat and might turn out to be useful for helping us to identify shocks and vector autoregressions. But many of the external instruments that have been proposed so far aren't real good, that is, aren't really highly correlated with the shocks, and we really have to be careful when we do inference with them. But we can be careful. There are methods that we can use for doing that. So I'm going to end on that, but I want to once again thank the conference organizers for this great event.
Any questions?
Very energetic. So I have a question. I'm curious about how do you go on and you construct these instruments in practice? So because the Romer and Romer are just dummy variables that were used before?
Well, so, I mean, two issues, right? So if one wanted to use the Romer and Romer dates, the indicator variables, the 0, 1 binary variables that you're talking about, you would use that as a set of instruments. You'd have zeros and ones, you'd have a 0, 1 instrument, right? That would be a differences kind of instrument, right? You look at a difference in two means, right? That would give you the thing. It turns out that the Romer and Romer stuff that we were using here were those dates modified, interacted with the size of the shock as they report in a later paper. So that's what we were using here, right? So, I should say, how do we construct these external instruments here? We don't, right? So what we did is when we went to the literature, found other papers that were written in which people had proposed what they called exogenous movements in monetary policy or exogenous movements in oil supply, and then we took the data from those papers and we used that as the instruments here. Now, one thing that's nice about this, I should say about this external instrument kind of way of viewing this is, even if you have a paper which, has some external instruments that are available from 1970 to 1996, and you've got a VAR that you can estimate from 1950 to 2011, you can still identify this. You can take your ETAs, right, over the sample period that coincide with the, external instruments and, estimate the various moment matrices there, right, and then estimate your impulse responses, et cetera, using the entire data set.
Here, I was wondering whether you are implicitly assuming that the external instruments are weakly exogenous with respect to your system, because in some cases, so they don't improve forecasting, including because some people augment the VAR with the instruments.
Sure. In the calculations that I did here, sorry, the issue you raise is an important one. It's going to affect the covariance matrix of this normal distribution that I wrote down, and that's going to be if these instruments are correlated with lagged values of eta or future values of eta, right? That's going to lead to some covariance between the sample covariance matrix of Z and eta hat and the estimated VAR coefficients that one would need to take account of. But that turns out to be reasonably straightforward to do.
One thing that I was wondering is you could run Granger causality test to check whether the instrument Granger cause your VAR.
Sure, yeah.
That could be.
I mean, that's fine. But again, the key thing here is these instruments can be correlated with lagged etas, right? And one can still use this approach. That might not be the most efficient approach that we're using here, right? But everything's still going to work. You're going to have just standard errors in the right way, though.
Mark, I don't know if you can, I was just curious if you could comment on these external instruments and the news problem, right? Because at some level, the obvious attraction of using history or these narrative methods is it lets you get your head around lots of information. On the other hand, you assumed, I thought, that the VAR was invertible. So is that incompatible with using those external instruments to help resolve the news problem?
Well, I haven't thought deeply about this. I mean, everything that I've done here, I mean, we need, eta is h times epsilon. So this is an invertible guy.
Right.
So this isn't going to help you solve an invertibility problem.
Right.
To solve an invertibility problem, I think what you're going to need to do is something like Domenico suggests, incorporate if these z's are helping you do that, you need to incorporate those into the structure, and then maybe it's invertible there or something. But I don't know. I mean, I think, another way of thinking about these z's, though, is that they're somehow, it's getting the timing of them right. I think they might be helpful for this new stuff, but I don't have my head around that yet. But that's a great suggestion, comment, question. Frank.
Yeah, I guess you could add additional identifying information by putting some restrictions on the age matrix, maybe not as much as you would usually do. Have you thought about that? And does that, I mean, that should sharpen the inference, right? So you've left the age completely unrestricted, but you could sort of say, I don't know, 2 elements are 0 or so, but I don't know what to do about the other ones. And
Yeah. Yeah. I mean, that would help. At the end of the day, if yes, that's going to help you, and that's going to change some things here. At the end of the day, if you're still relying on the Z thing, to identify some element of H that's going to be important for some impulse response or some variance decomposition, right? The weak instrument thing is going to dominate. The sampling uncertainty that comes from weak instrument is going to dominate the usual, root T sampling error, right? So you're still going to be facing these problems, right? They just show up. They're still going to
so
be.
I guess the main issue is the denominator, right? That, if you could do anything to, prevent that from going to 0 and solve this normalization problem that you're using with the division.
So it's the denominator for the impulse response thing. It's that denominator for the historical decompositions, and for the variance decompositions, it's that matrix that came from God, right? And that's normalization free, as you might imagine, right? So it's not just, it's the normalization for the impulse responses, but not for the other guys.
I have 2 questions. So the first one, can you tell us a little more about robust methods? What are you thinking about? You can imagine more complicated models. And the second question is, for example, when you have hack structure, for example, typical tests would be biased. How do you handle that?
Yeah. So I don't have good answers to those yet. I think the hack stuff turns out to be reasonably easy to handle here. Not for optimal inference, but for robust inference in ways that you certainly can understand. So I'm going to just talk to you for a second. Okay, so here's the limiting experiment here is just a normal with a mean that you don't know, that you can estimate, and it's finite dimensional. It's small. It's like 6r by 1 here, right? And all of these objects that we're interested in depend on that mean. So you can just construct a confidence set for that mean and invert it to find confidence sets for everything that you want here. So that's one way to do robust inference here.
Any other questions? Let's thank Mark.